Thank you for coming. In the years since Twitter decomposed its famous, massive Ruby on Rails application, a system that we affectionately called the monorail, we built and operated a massive tweet fan-out system that today, on average, is delivering about 20 million tweets a second to followers' home timelines. That results in, after accounting for filtering rule sets, almost 2 trillion tweet deliveries a day into home timelines, and that, in turn, is backed by a custom Redis caching cluster that's operating at the rate of 150 million Redis operations a second. So it's pretty impressive. And what I'm going to talk about today is an evolution of a system at Twitter, away from a model that prioritized that system and the low latency of delivery, with this goal in mind, which is showing people the best possible content on Twitter all the time, and ideally as effortlessly as possible. And that work is framed within this context, which is that is being built within an architecture optimized for nearly real-time tweet delivery to followers' home timelines. And in case there's any ambiguity about the product I'm talking about, this is what we call the home timeline. It is the primary tweet consumption vehicle for tweets on the Twitter platform. It is the first stream of tweets you see when you open the app. It's also known as just the timeline, the Twitter stream, the news feed, the Twitter feed, and so on. But they're all referring to the same thing, which is a sequence of tweets from accounts followed by the viewer, and typically in reverse chronological order, with the newest at the top and the oldest at the bottom. So to understand the background of the system that we're working on changing, I'm going to discuss tweet fan-out a little bit. And the high-level summary is this. It's a lot of pieces I'm going to abstract away. But when a new tweet is written to Twitter, tweeted by a user, it enters our backend system, and there's several execution paths that handle that tweet. The first is a synchronous path that, among many other things, persists that tweet into a database layer. That's Manhattan. My colleague Boaz did a talk about Manhattan earlier today, and it was great. Upon successful tweet persistence in Manhattan, it triggers an asynchronous execution path. That asynchronous execution path delivers the tweets at high volume to the home timelines of target users, in cache, in memory, without any disk persistence for the home timelines. And all of the RPCs that are powering the system are all done at Finagle, which is an open source RPC framework or distributed systems toolkit. And my colleague Moses spoke with that earlier today too. So these home timelines are in cache. They're powered by a custom Redis cluster fronted by a Scala service built internally. The customizations to this Redis cluster enable us to perform huge volumes of asynchronous batch writes, which is why we hacked the Redis in the first place. And from the perspective of any one viewer of any of those home timelines, it looks a lot like this. You have new tweets at the top, old tweets at the bottom. They come in from the top. You can request new tweets, and they're continuously and asynchronously filled in. And this model is not unique to Twitter. Many organizations and companies that enable users to follow each other and perform actions on that network and then aggregate those actions in some fashion tend to do something that looks kind of similar to this. Perhaps the more unique thing about Twitter's situation is the scale at which it's operating. So on average, we're doing thousands of tweets per second with spikes well over tens or hundreds of thousands of tweets per second, depending on the circumstances, which equates to, as I said, around 20 million timeline deliveries per second. You can kind of think about this as the tweets per second that are written to Twitter times the density of the follow graph of the users that are using Twitter accounts, minus, as I said, filtering rule sets. And we can do the deliveries in the 99th percentile at about 1.8 seconds, meaning that 99 out of 100 tweets are delivered to users in under 1.8 seconds, with a median at around half a second. So we worked long to get those deliveries down as low as possible. And the end result of that is an architecture that looks something like this, zoomed in and at its most simplified form. We have some API services on the left-hand side. Users issue reads for their home timelines through API services, which go to the timeline service, so named because it serves timelines. We're a microservice architecture, generally speaking, at Twitter, although I'll talk about that a little bit later. The timeline service for the home timeline, which is the main tweet stream for the user, reads from the timeline cache, and that is, of course, asynchronously updated at tweet time by the fan-out service. And this system has a lot of great benefits. First of all, it's very scalable. If we want to simply deliver more tweets, we can add more cache, or we can add more fan-out instances. And it keeps things very simple. The system only needs to go to a single place to determine the content that a user will see. It's pre-computed, it's pre-assembled at write time. We're going to fetch all that data, perhaps filter some stuff out of it, and then send it back to the API, rendering it for users. And at Twitter, we prefer to keep things historically simple for many reasons. But there's some limitations about the system, and that's what I want to focus on today. I'm going to frame it around 3 broad categories of expense, flexibility, and relevance. So the first problem, expense. You may realize that that system implies, with its 20 million or so deliveries per second, is doing a lot of write operations all the time. It doesn't even matter if the target users who we're delivering tweets to are using Twitter at that time or not. We're continuously doing work. That, of course, implies that not every write by the system is going to be read by the viewing users. And lastly, and perhaps most importantly, it doesn't actually eliminate complexity on the read path for these tweet streams. If I zoom out from that earlier diagram, it begins to look a little bit more like this. So as before, API services, a timeline service, a timeline's cache, and that's the same. But the timeline service on the read path must also consult other services. Graph storage, databases, user services, tweet services, for various circumstances, whether it's filtering, whether it's for respecting real-time visibility rule sets, such as blocking users or muting users or so on, or for handling things like cache misses. We get to pull in all kinds of data from different sources to repair the data missing from cache. There's still a lot of complexity in the read path. And then, of course, when it goes up to the API layer, how it's structured at Twitter, the API services have to do a lot of this work all over again. They have to go and get the user objects. They have to go get the graph objects, the tweet objects, fetch them all again, do a bunch of stuff with them, and then render that out through the API. So the system is still complex. Flexibility is another issue. That system implies that there's a lot of data living in cache for a very long time because it's assembled at write time, and we don't know when the user is going to read it. If users have very low velocity tweet streams, perhaps because they follow few users or few not very active accounts, the data that is written to their home timeline in cache can potentially persist in memory for a very long time. That implies all kinds of problems with codec versioning and cache invalidation, and you need to construct jobs to wipe caches if you want to have a clean state for a new codec or key version. And this also means that the ordering criteria for the final result, which is the reverse chronological home timeline, have to be available at the right time of the tweet. So we can't defer the delivery of this tweet because we have everything we know about the ordering of the timeline happens when it is received. The author, the recipient, and the time which is tweeted. This operation, performing at write time, also focuses more on the author of the tweet rather than the recipients. And that kind of plays into the limitations of relevance. It means that when we construct the main feed for a Twitter user, the content that they see is determined exclusively by network actions of that account rather than anything that we know about the viewing user themselves. The follow graph weights for the accounts that they follow are equal, they're static. It doesn't matter if users interact with one user more than the other. With the way that that system is historically been designed, what determines what the user sees is entirely dependent on when it was tweeted and when the user logged in. We can't give preferential treatment to users that maybe they're close friends or close ties. Lastly, if we want to do any sort of algorithmic improvement to the timeline constructed at write time, it's very awkward. We don't know if we're going to get it right. We don't know when the user is actually going to log in and see the data that we've perhaps applied expensive relevance operations to at write time. So given all that and this goal, as I mentioned before, which is showing users the best possible content, maybe we want to move to a tweet stream that looks a little bit more like this, where perhaps it's composed of data from multiple sources, chunked into different kinds of sections. We have ranked tweets from accounts that the user follows, maybe outside of chronological order. Recommended users to follow rather than tweets, meaning that it's no longer just a tweet stream. It's more like a Twitter entity stream, a collection of objects from different accounts. Recommended tweets from outside of the user's following network. And lastly, you can still throw in some reverse chronological tweets to keep the real-time feel of Twitter alive. And that's where I'm going to talk a bit about scatter gather, or as sometimes we call it, response fan-in. As anybody who works at a large organization knows, organizations develop lots of weird internal language that don't always resemble the realities of what that language means. Twitter, we love to say fan out. We fan tweets out. We fan out notifications. We fan out emails to teams. We fan out for lunch. We just fan out everything all the time. And as a result, the inverse of that we often call fan in. And what that looks like is this complicated graph here. But if a request comes in from the API or some sort of aggregation service at this layer, it is going to scatter requests among a variety of content services that are logical units responsible for assembling content. And then at the very bottom here, we have content sources. And many of these content sources may be shared between content services that perform overlapping kinds of data recommendation. And of course, once the processing is completed, we fan in all the responses from all the content sources, assemble something in the aggregation service, and send it out through the API to the clients. So with Scatter at Twitter today, we consult a variety of content sources upon the user's request for their timeline. And we also integrate relevance and prediction systems into this workflow, which is a completely new concept as far as the home timeline is concerned. So for example, some of the sources that we consult when a user opens up Twitter and looks for their latest tweets, we'll consult the search index, which is a very large dependency of this new system for collecting unseen home timeline tweets. The search index at Twitter is a very impressive system. It has billions and every tweet ever tweeted is available for retrieval via the Twitter search index with a lot of scoring features and ranking information that we subsequently use. Recommendation systems for recommending both content from accounts that the viewer may follow or not follow. Moment services, if you're familiar with Twitter Moments, there's a lot of moments-related data that we can pull in from those services to make recommendations. Trend services for figuring out what's trending and what tweets in the network are related to that trend. And finally, of course, machine learning-based ranking systems. Sorry for the flaky projector. Okay, so that all sounds great. What do we do to build all that, given the constraints of this problem, which is a system designed for real-time tweet delivery? There's a lot of challenges imposed by that. The first is figuring out how to reorient the entire architecture of the primary tweet consumption vehicle for tweets at Twitter. We have to insert a lot of complex new services into the read path for the home timeline that hadn't been there present. There's a lot of load imposed on that read path, and teams and services that operate those services maybe hadn't been exposed to kind of requirements that implies. We have to decide what to show the user if there's multiple candidates available for selection in the response. We also have to figure out how to keep the real-time nature of Twitter alive as we can deliver tweets in under a second to a home timeline. And finally, public API compatibility. There's a lot of third-party clients that use Twitter API. If we rewrite everything, we have to make sure that those clients still work properly. So here's some things that we did. The first thing, sorry for those in the back, layer complex read-time components on top of the right-time composed home timeline results. So start by saying we didn't actually throw out the old system and build something new. We simply augmented the existing system with a lot of complicated read-time logic, and we slowly ramped that up. This meant that the years of business logic we built into Twitter for serving reverse chronological timelines that they had been for many years remain completely intact, and that real-time tweet results, as constructed by our fan-out system, continue to be available as a source of content. So a very simple and zoomed-in diagram of what that might look like. We had some new APIs on the left, existing APIs on the right, and these APIs interacted with existing logical units of home timeline of the timeline service that serves the home timeline. And both of these logical layers were operating within the same service container. The existing APIs interfacing with the existing logic meant that the third-party APIs did continue to work as they did before without any major modifications. It also meant that we could tiptoe into core relevance products without having to invest a lot of upfront work in redesigning a system to meet all those criteria from the ground up. So we operate on microservices at Twitter. You could probably imagine what happened next after we did all this work into the timeline service. We broke it into two services for resiliency purposes and iteration speed of the logical components that were contained within that service. So we had a lot of new people joining a lot of teams, writing a lot of code to do this new work into the timeline service. It was destabilizing, disrupted its other core responsibilities for serving tweet streams for various other products, profiles, tweet detail, conversation pages, notification timelines, and so on. So given that diagram, we cut it in half. On the right, we have the timeline service that continued to do all of its prior work. And on the left, we have an aggregation service that we simply call the timeline mixer. And we connected the two with an RPC. So that allowed us to isolate the read-time workflows into this new aggregation service. And we could independently profile, tune, and monitor that service independently of the more core work that the older service was doing. The failures that we suffered from that system, completely isolated from the much larger, older core service, and a service layer that wrapped the timeline service on the read path allows us to continue to consult reverse chronological and fanned-out home timelines as a source of content, along with many other different kinds of sources that are available. And two services doesn't mean double the code. We basically pulled core idioms for representing and serving timelines into a common library shared between these two services. So in reality, there are thin service containers wrapping that core logic. So once we had that separation on the request path present, we began to integrate partnering services and the introduction of state into the serving path for home timelines at Twitter. It formalized this new layer as a real-time aggregation layer for logical services operated by many different teams and the products that they are putting into the home timeline. So zooming out from this diagram a little bit, it begins to look a bit more like this. So we have API services on the left. They direct their home timeline requests to this aggregation service, the timeline mixer. And it still has an execution flow that looks as it did before, where it interfaces with the timeline service and the timeline's cache. But it also scatters requests to many other content services represented by these green circles. And all services in distributed system environments have dependencies. What happens here is that there's a large number of very complicated services that are consulted at the same time in the request path. We execute requests to all of them simultaneously, and we ask to pull in data from all of them, at least the services that are able to provide data for that user at that point in time. So to make that a little less complicated, we developed a framework for easily integrating all the different products that are available at Twitter into the home timeline and able to experiment with them. And the introduction of state into the request path was necessary for enabling things like pacing to make sure we don't serve similar things too frequently, and also for deduplication of those recommendations. You don't want to serve the same recommendation numerous times. Thus, this service began to get very complicated, as it was one of the few truly stateful services that serve consumer products at Twitter. We also built in a lot of aggressive request filtering and user targeting to bypass the expensive collection of all this data at request time and fell back to the reverse chronological timeline. We'd only actually execute this expensive workflow when we believe it would have maximal impact on that particular user at that particular point in time. Otherwise, there's little value in exerting a request load on all these other dependent services. So once that happened, we began to onboard a lot of different teams and a lot of different services into this aggregation layer. We began to realize that building ad hoc relationships with the teams that operated all these services began to get very expensive. So in large organizations, there are often many teams, and these teams have different backgrounds. They have different levels of technical debt in their services. They may not have services at all. They may have different requirements for team operation. And so it's difficult to negotiate on an ad hoc basis what the responsibility of team A will be and the responsibility of team B. So we developed sort of this hard contract that we would impose on all of our relationships going forward to simplify that and simplify the division of responsibilities whenever we pull new content into the timeline. So an example of some of the things that we imposed were that we would place core business logic for all these new consumer products into the remote services themselves. So when you have aggregation type services that pull data from many other sources and assemble them at a certain layer, it's very easy for logic, business logic, to bleed across service boundaries and bleed across team boundaries and put it into this aggregation service. The reason being is that maybe it's like less capacity on some team to put some core targeting logic in the aggregation service, or maybe that other team doesn't have a service and they don't really want to operate one. So by imposing a contract such as this, where an external team must have a service and they must own all the business logic for that product in their own service, it prevents us from assembling an ad hoc service monolith within our team that becomes impossible to maintain, impossible to understand, and impossible to operate. On our end of the contract, we had to ensure, for example, that we would make callbacks to those remote services whenever their content was selected for inclusion in the home timeline. And that's because those teams may need to update models, update fatigue, or do various other things once their data was actually selected for showing in the user. Those teams are also responsible for building and maintaining a data model translation layer in this aggregation service, which is really the only code that they're responsible for writing and maintaining in this aggregation service. The reason for that is that nobody knows the data models of various teams and services better than those service owners themselves. So they map their data models into very simple timelines data models that we can understand. And thus, after that mapping is complete, we understand how to easily assemble a timeline and decide what to show the user after the fact. Okay. Some other things that became important, obviously, were to degrade and drop features if they became slow or if they failed entirely. Latency is probably the most difficult thing to diagnose in a distributed system. You don't know if it's because of network congestion. You don't know if it's because the service is in GC. if it's encountering actual failures, if some like second or third order dependency of that service is failing and they have like weird characteristics when they're being slow. So we basically define tiers of services, critical services and non-critical services. And services in the non-critical service tier have an enforced minimum latency cutoff and also uptime requirements that we impose on them. The great thing about recommendations is that a really good recommendation can be served at any time. It doesn't have to be served with the immediacy that users expect when they want to see a tweet from 1, 2, or 3 seconds ago at the top of their home timeline. And thus we can be a little bit more flexible when collecting recommendations of content to show users. Sorry. So if you imagine that solid lines here are perhaps critical dependencies and dotted lines are non-critical dependencies, we'll have some critical dependencies in this request path. When a node fails, like this green circle highlighted in red, we can simply drop it. And we can do that using the framework that I mentioned earlier. We sandbox requests to these content services so that when they fail or when they're slow, they're automatically dropped. We can also adaptively elect to bypass a collection of content from that service entirely if we believe that it's unlikely to succeed based on the historical characteristics of that remote service, but also depending on how much time is remaining in the current request before it's actually canceled by the caller. In the very worst case, where all of these other content dependencies are completely broken, we can fall back to the reverse chronological timeline and serve that. The reason why we define these sort of service tiers is because when we onboard a lot of dependent services, it's very difficult to understand how each of these services works in isolation. Those services, especially if they're complex services that power large products themselves, also have a large number of dependencies. Sometimes they share dependencies, which can appear like cascading failures, but in reality, a common second-order dependency has failed and is manifesting as many immediate dependencies failing. So we basically treat them all the same. So an important resiliency thing that we learned at Twitter is to implement, respect, and propagate back pressure signals. So what I mean by a back pressure signal is an exceptional condition that indicates to a service caller that a deterministic failure is present and a subsequent retry will not succeed. Typically, those are load-induced latency or failures. They can also be database hot shards. It doesn't matter how many times you retry on a database hot shard. It will not recover until load is relieved. And so a back pressure signal is effectively a fail-fast signal that tells all callers to not even bother retrying and fail as rapidly as possible. And ideally, that signal is propagated all the way back to the call chain so that grand callers or third-order callers actually are not retrying on your service and making it even worse. So if we propagate a back pressure signal from the timeline service to the timeline mixer, it fails fast and actually fails immediately and throws that back to the API to fail there. And then that will just show the user an error right away, rather than trying to create some sort of cascading system failure because of a retry storm, where instead of handling normal load, the degraded service is now handling 3 or 4 or 5 times the load and is clearly never going to recover. Some general principles that we live by are things like minimizing code delta between deployments and making everything configurable at runtime. So we deploy often, every single day, multiple services every day. And whenever possible, we ensure that the state of the service post-deployment is the same as the state of the service pre-deployment, meaning that we don't need to worry about changes in the behavior of that service as it is rolling out, which is another thing to worry about. Features can be enabled or disabled by engineers or operational teams when they're ready to do so and when they're waiting for it to happen, rather than having to determine at deployment time if something is going wrong. Rollbacks are expensive. Depending on your organization and the kind of protocols you have in place, a rollback can simply be a pain, or it can require some sort of operational post-mortem, or in the worst case, something has gone terribly wrong and your new version of the service has written data in a new schema somewhere, and then after rolled back, it can't read it and everything is broken. So try and avoid rollbacks whenever possible. And lastly, we do a lot of A/B testing. The reason for that being is we know that intuition alone cannot be used to drive dramatic changes in Twitter's core product. Products that are introduced into this retime aggregation that don't drive core user metrics, but actually increase the complexity of the system are dismantled and removed. They have to have a positive and measurable impact on the core Twitter experience. So with all that in mind, I'm going to discuss one of the specific workflows of this new system. It has been popularized as the algorithmic timeline, but we call it internally the rank timeline. I'm going to talk a little bit about how that works. We recently began to introduce relevance augmented home timelines of users based on tweets that are from the accounts a viewer follows, but perhaps not necessarily in chronological order or from long in the past. The tweets in the timelines that are powered by this feature are largely sourced from the Twitter search index, and we treat that largely also as a tweet feature store. As I mentioned, it's very extensible. It has a lot of data, has all the tweets in the search index, has a lot of scoring features that can be used to figure out what tweets are relevant for a user. So the way that works is we do a first pass ranking from search to figure out what tweets has the user not seen. We go get them. We ask the search index to score them and give us the best ones that it thinks from that corpus. We then take all that back along with various features that can be used for subsequent ranking paths. Throw that into a second layer ranking, and we call that engagement prediction. It's a series of services that run with a machine learning trained model in it that can do a ranking on a series of data with the estimated likelihood that a user will engage with that tweet or user or anything else. And then finally, after that ranking pass, we take the best scoring ones, we join them with reverse chronological timeline, and we serve that back through the API. So there's several steps involved here, and I'll outline it here in a diagram. So the initial request from the user for the ranked timeline comes into the API. The timeline mixer scatters requests among many services, but the ones related here are the timeline service and a search service. The search service itself does its own scatter gather against the highly partitioned search index. It fans in all the results from that operation. It joins it with various state from user session state storage, from feature storage that can be used for ranking. It pulls in the reverse chronological Twitter timeline. It pulls it all back into the timeline mixer. It performs that first pass ranking cutoff. And then with all that joined data, it passes it off to the second layer ranking service, which is our prediction services. And they, again, score the tweets by the likelihood that a user will engage with it. And this introduced some interesting resiliency problems because the bottleneck was not as you might think. It's doing a lot of complicated ranking and scoring, but the problem in this system was actually network bandwidth. It was not actually compute. Finally, after joining all that stuff, the ranked timeline with the reverse chron results, we serve it through the API. And so you might notice from discussion about several layers of ranking that it looks a bit like a funnel. So at the top, we have the potential, the corpus of all possible tweets. They go through a first pass ranking based on signals from the search index. They go through a second ranking based on features from the engagement prediction service, and then the final assembly, which is served out to users. It truly is a funnel, because there's some numbers here. So we'll execute hundreds of billions of, collect hundreds of billions of tweets from the search index every day. About 5% of those end up being selected for engagement prediction. And then out of that, we serve about hundreds of millions of tweets for delivery back to users every day. So that's kind of the scale of what it's like today at Twitter. And this system continues every month to serve more and more ranked tweets from the system as we get better at doing it. So some lessons from this whole process. The first is avoid the team as a service trap. So as I mentioned, we're a microservice-oriented architecture at Twitter. What that tends to mean at Twitter is that there's a team that operates a service. So if you have team A, they operate service A. And as team objectives and goals tend to change, the team often feels compelled to put the new workflows for the new tasks into service A, even though it might not make sense. So I mentioned earlier that we began to put all this work into the timeline service because as the timelines team, it made sense, seemed like the right thing to do. But in reality, it was an operational nightmare. And from the start, if we had put it into a new service on its own, we could have avoided a lot of the resiliency problems that had come along with it. So model teams after problems to be solved, not implementations of solutions for those problems. Second is establish team clear responsibilities for boundaries amongst teams. It should be very clear up front when you're partnering with other teams where the division of responsibilities is. Without that clear demarcation, you risk bleeding business logic across services and creating unsustainable monoliths or worse, unknown code and unmaintainable code. Of course, interfacing with lots of services means interfacing with lots of people. Large numbers of read-time dependencies are very difficult to reason about. Not all dependencies can be critical. It makes a lot of sense to define service tiers in your architecture, things that can be served or cannot be successful. We cannot successfully satisfy the request without serving data from this request path, and a tier of data that could be degraded in some sense that would still provide a reasonable experience for the user. Iteratively filter input. to reduce the cardinality of expensive operations. You have this much data and you have a very expensive ranking system. Perhaps you could actually just rank this much data if you could filter out a lot of reasonably simple stuff from that corpus. That's how we are able to move from a system that is doing 20 million home timeline writes a second to serving ranked timelines for most users at Twitter all the time. So save expensive or latent resources for the operations that truly need them and have the highest impact for the result of those operations. And lastly, fail fast on critical dependencies if they indicate to do so. If you build a back pressure type signal into your system where you can propagate failure for deterministic problems back through the system, you'll avoid cascading failures which harm not only your services but the rest of the company as well. That's everything I have, so I'll take questions. Yep.
But it seems like you didn't really replace the fan-out service.
Yep.
Is that, would you like to do that, or do you still think that is the foundation of having a fast retrieval of your timeline?
Okay, so the question is, I discussed some limitations of tweet fan-out. Why didn't we get rid of tweet fan-out, and why did we just build more stuff on top of it? Is that pretty much?
Yeah.
Yeah, okay. So the reason for that is because although the tweet fan-out system is very expensive, and as I said, it's doing a lot of operations all the time, it's taking up network bandwidth in the data center, et cetera, it is remarkably stable because of the effort put into making that system stable over many years. And so it's not actually a large source of operational pain for us. And the fact that it can deliver tweets so efficiently means that using it and the timelines that it powers as a content source is still very valuable. So this complicated retime system does work very well, but there's latency implied by it. So in order to have great recommendations, you typically need to accumulate enough information about those recommendations for them to be useful. So that system implies it's much less real time than something that we organize simply by the criteria of the time was tweeted. So users still find that to be very important, and so thus we keep that system in place to satisfy those goals. Give an example of a back pressure signal? Okay, so perhaps a classic one is one we use to indicate that, for example, in our timelines cache, we actually define empirically a maximum number of Redis commands a second for a particular key in that cache cluster. And once we exceed those Redis operations per second, instead of attempting to satisfy the request, we simply will throw a back pressure signal to the caller. Doesn't matter who it is. And that back pressure signal basically says there's too much load for the system, and retries, if you retry it, there'll still be too much load in the system, so fail fast. So that's one example. And we have many other variants of that for all kinds of different caching systems. It's not unique to our Redis implementation. We have those signals in place for our sharded MySQL databases and other things. And so many high volume services or services have a lot of critical dependencies all have variants of this back pressure signal, and it's universally respected within the system.
How do you measure the engagement of some particular tweet?
How do we measure engagement from a particular tweet? I'll talk to you about that offline if you don't mind.
The back pressure and giving up on some dependencies. Was there anything else, or were those the ways that you maintained your latency requirements?
So how do we maintain our latency requirements? Is it largely about back pressure, or is it about giving up on unhealthy remote services? It is definitely both of those, and some of that determining how long we're willing to wait for a recommendation for content is part of that contractual negotiation process that I mentioned. So many services have all kinds of different requirements. They're often imposed by the design of the systems. And so we will indicate to a team how long we're willing to wait for their data. And they try to make the service work accordingly. But regardless of whether it's successful or not, we'll define a hard limit for a class of services that we consider to be non-critical. And whether that timeout includes retries or doesn't include retries That's the maximum amount of time that we'll wait for that response. Does that answer your question? Okay, thank you.
The content services, is there any, how do you propagate information back to them? So if you have particular content services problematic and you're frequently dropping them from your content collection, how do they know that do they know that their service isn't providing as much value to the user? Like,
Yeah.
are there risk at being disbanded?
All right, that is a great question. So the question is, we have all these dependencies that provide content and recommendations for inclusion in the timeline. If there is a particularly unhealthy or low-performing service that isn't responding with content adequately, how do we give them the feedback so that they know that it's a problem? I would say today we don't have a great automated way of doing this. I think that they can imply that that might be the case by measuring the engagement on their recommended content as seen by users as compared to others by a system that I'll describe offline. But largely it's ad hoc and communicated by the team operating this aggregation layer. If they know that the success rate for content retrieval from service A is way below the bar or where other services are, it is often a matter of manual communication. But we do track, even though we consider them non-critical, we track the success rates and delivery success rates of all of these content services ourselves.
Do they use a success rate for that initial signal? Could they determine their own success rate for inclusion based on?
So could they infer their own success rates? So services that ask us to actually provide callbacks to those services after we include content from the recommendations, if they would like us to do that, then they would be able to infer we're not actually choosing their content because they are simply not getting any callbacks. But otherwise, they would have to collect it via an offline manner. Yeah. Yep.
Are your timeout times static, and how did you figure them out? Is it like we arrived at this thing based on guessing?
Okay.
Figure it out?
So are our timeout times static, or was there a lot of process involved in determining how we set them? So they are often static. They are not static if we do a calculation in the service. So once we get the request, this aggregation layer does a bunch of work. That's critical. After the critical work is completed, we actually calculate how much time is remaining in the request to respond successfully to the caller. As you know, this service has timeouts, and many other services on the call chain also have timeouts. So we perform that calculation, and if we think there's adequate time, then these other services are called with a static timeout. If there's not a lot of time, then we actually modify the timeout. We reduce it. We say we're actually only willing to wait 50% of that time to collect the content from the services. Often they can't get back to us in time, but sometimes they will. And then once it actually decreases below a certain level, we'll actually say there's absolutely no way we're going to get anything back from that service, and we bypass the collection of that content entirely. So it is largely static, but in various cases, mostly involving like timeouts and latency, it can be dynamic, depending on the state of this aggregation layer when that call is executed. Does it answer your question?
Yeah.
Okay. Oh, and sorry, and we arrived at those timeouts based on, we looked at the latency profile of this existing system before we did all that work. And so we imposed timeouts that kept the latency profile largely to the same amount of time. Yep.
Do you find it a good to communicate to the teams that you're partnered with the requirements and expectations for them? Do you just big meetings? Is there some sort of documentation?
So how do we communicate to these teams that we're interfacing with, what the expectations are? We do provide a lot of documentation. We also provide a lot of examples and prior art for previous integrations that had either gone successfully or unsuccessfully. And as for the ongoing relationship, we communicate the more operational aspects of our interface between our services. But also these teams are able to gauge the success of their products based on how successfully we can actually get it shown to users. And if there's a problem there, then they're able to infer it from their own metrics, as those teams and services largely operate all their own business logic in their own services.
If you can dynamically change the amount of time you're willing to wait, I don't know what the politics of Twitter were like before, but this aggregation engine kind of seems like it's a very powerful political tool.
Okay, so the question is this aggregation layer a powerful political tool now that we can selectively include or not include content from other teams and services? I think sometimes, but sort of the upfront contract states that the ultimate decision for inclusion in the response lies with the team operating this aggregation service, and that the things that indicate success for a new initiative that requires a new integration into that system require like a global metrics improvement. So does that answer your question? So there's no metrics that exist that only satisfy the goals of the team operating the service. The success metrics are like company-wide metrics improvements.
I think that answers the question. Like, if you can't show customer value, if you can't show user value, then it's a justifiable reason to.
That's right. It has to show the user actual value. Yep. Any other questions? Okay, thank you.